I'm Haroon Sheikh. I manage the core animation of the Quartz team. And we've got a great session for you today. We're going to be talking about a great new Leopard innovation called core animation and see how you can actually get that into your application. So many of you were already in the session before this, so this is going to be follow-up on most of that same content. And for those who are new, we'll build up on some core fundamentals like, introduce core animation, the layers themselves, talk about the animation model, and then the bulk of the session will actually go over the core animation APIs, and we'll have a few demos through the session itself. So, it should come as no surprise that over the last several years, we've got this evolution going on in terms of the user interface itself. More and more applications are requiring seamless compositing. You've got animations and transitions going on. A lot of the content is actually quite dynamic in nature, and the UI is actually getting, providing a much richer user experience. So just wanted to talk about an example from Tiger. We've got the iChat U+3 as part of iChat AV, and you've got QuickTime sources coming from multiple sources, and all of that's just animating over time really seamlessly, with great frame rate. iTunes Coverflow, you've all seen that. Everyone's used to it. And it's a great way of visualizing your data through your artwork, album art. Finally, you've got full-screen applications like Front Row and consequently Apple TV itself, where you've got great content coming through from the web, from your main machine, and just being presented in a nice and great way in terms of layers sort of moving across the screen and with the right quality of animation as opposed to too much animation in your face. So I'll have a lot more examples of this stuff in Leopard. You've already seen some of these at the demo, in previous demos and in the keynote itself. But what you really should recognize is you really want to be part of this wave of applications that are moving into this new era. And the way to do that is really you want to rethink the way your applications work that portray your data and sort of re-examine how you can portray your data with some, hints of animation or, just so the presentation is actually really nicely done. So and part of the reason is you really don't want to be left behind as your competitors or just the rest of the OS sort of moves in this direction. Trying to get some of this content done is relatively not hard, I would say, but it's just that in the past you've had to go down to the OpenGL level. Most of the examples I showed you already, basically they had to go through to a step of making sure that they could take advantage of OpenGL efficiently, uploading textures at the right frame rate, at the right time to get that seamless animation through the system. And that's where we actually decided, let's bring all of the fundamental things in terms of core animation that those animations applications provided, and let's bring that into the OS and provide that as a service to you so that you can do some of those same things. So core animation, you've heard about it already, but the key thing is it's actually a foundation for both compositing and animation. So you could even actually use core animation for the sole purpose of just layer compositing. And that's a great functionality in itself, and on top of that, you can actually animate that content. So it is part of the Quartz core framework, and very similar to what you heard already in terms of all of these layers that you briefly were mentioned in the previous session are very analogous to NS views. The content of these layers can come from lots of different sources. We talked about those already in the previous session, but it could be Quartz content, it could be OpenGL content, even core text, all sort of coming into the picture. You can apply a bunch of layer effects to that, shadow effects, masking effects to get really rich content. You've got these layers, and now the thing is, the key thing about core animation is it is a declarative animation engine. As a result, you don't have to sit there and program every frame of your application. The examples I showed you, they effectively had to do that they had to go through and actually position all of those layers or their concept of layers and objects and textures at the right location at the right time. And whereas Core Animation actually abstract a lot of that for you, and actually you can use it without having to worry about much of the details. So in terms of the architecture, Core Animation is the center, but the key thing is it's sitting on top of OpenGL. So to answer the question that was there at the previous session, Core Animation sits on top of OpenGL, but it actually can use all of the Leopard-supported graphics cards. So it's actually not restricted to programmable GPUs or anything else like that. And that's a key reason why you might actually want to use Core Animation itself. In the past, you may have had to go down to OpenGL, but trying to get it all done right and correctly, with the right texture formats, uploading it at the right time, looking at all the hints and tricks that you need to do there. Now you can actually use Core Animation itself, and it will worry about all of those details. So, like I mentioned earlier, if you just use it for the compositing part of it, I mean, that's a great step forward, and it will just work across all the graphics cards supported by Leopard. We've got all of the other Quartz and media technologies, such as QuickTime, also being utilized as part of Core Animation itself. And then fundamentally, you can actually also use it at the core code level. So our goal was to actually get high quality and high performing animation. So you want to be able to hit that 60 frames a second frame rate. We do that by actually making sure that your application does not have to redraw often. Ideally, you are not actually drawing every frame. So much of your content is actually, you can draw it once. Core Animation will actually buffer that content up for you, reuse it again and again, unless you specify that you need to change that content. When you're resizing, when you've got a layout going on, you're moving things around, for the most part, things are not necessarily changing in terms of the content. I mean, they may be animating in terms of movement or repositioning themselves, but the content itself is not necessarily changing. So ideally, in that case, Core Animation doesn't necessarily have to call back to you. You've got text layout, text views, or anything else like that. Yes, they do need to reflow appropriately. But here's another way where we can avoid calling back into the application code itself. And we can actually eliminate some of the code that actually requires you to run at the frame rate. And that sort of gives us that performance boost. And you've heard in many sessions previously that Core Animation is taking advantage of multi-core functionality through multi-threading. And it actually runs a complete rendering on a separate thread for you. Talked about layers briefly, but what are they? And I'll just go through an example, a very simple one. But you've got a photo in one layer, another text layer on top of that, followed by a graphic overlay, which is yet another image maybe. And as far as what the user sees, it's just this is your composited result on top that gets presented. These layers can have content coming from multiple sources. We've talked about core text. OpenGL content can be, you can actually draw through a GL context itself. Of course, composer compositions can be placed as part of these layers. You can actually capture movies from QuickTime and also, at the same time, play back movies. Quartz 2D images, in terms of being able to set a layer's content to come from an image source, is actually quite useful and actually quite used in the system. Also, you can actually draw your own content through Quartz 2D itself. Another point about layers themselves are that they are quite lightweight in nature. So you've seen some of the demos and examples. And last year we had a demo that showed 6,000 layers sort of animating. I'll have a video of that for those who haven't seen that. But the key is, these are very lightweight data structures, so that and our goal was to make sure that you can actually have thousands of these in the system. Layers can have transforms on them, and we do that basically by allowing a perspective transform, which is a 4x4 matrix. As a result, you can actually get, depth sorting is handled automatically for you. One thing we do not support necessarily is the ability to have layers intersect. And so that's an area that's not defined. But that doesn't stop us from doing great animation like this particular one from last year. So I'll let that go for a little bit. But you've got lots of layers present there, all animating. And over time, you've got a lot of this animation is done through this concept of hierarchy of layer tree that you sort of modify the root or the parents, and everything sort of follows from that. So this layer tree, you've got these layers, you want to define them into a tree. And it is a very simple concept where every layer can have a sublayer. As a result of that, you can actually construct a tree. It is a back-to-front compositing model in the sense that the next thing you add will be composite on top of what was there previously. These layers can have core image filters applied to them, onto their content itself, and also onto the background. So the example on the bottom right sort of shows a blur effect being applied to only a portion of to the background, but sort of restricted by the layer's mask to define the area of effect. You've got layers now in a layer tree. Now you want to actually animate them. So there are a lot of layer properties that you can animate. We'll talk about all of those properties a little later in the session. These animations are configurable, in terms of what the timing features from a particular point to another point, specifying the duration. You can also customize all of that, apply a keyframe to it, apply it along a path, transitions on them, animation groups. So a lot of this was actually discussed in the previous session. The other thing you might want to do with this layer tree is the layer tree is animating, but you may want to find out what's the current value of a particular property. And so we provide a way to query the animation status, and it's really useful for hit testing purposes. One key thing to remember about animation itself is by default, when you change a property, you are triggering an implicit animation. And let me talk about that a little more. So here I've got a simple example of the core animation icon in a layer, effectively. And all I really want to do is set its opacity value to 0. Your code executes, and effectively what that means is, as far as you're concerned, the opacity value is 0, but it's actually occurring over a default time period. So it will actually fade out over its default value. Similarly, we've got this concept of transactions. You want to make sure that all of these operations are being done in an atomic update. So I've got a few more layers here. And what if I wanted to set its opacity to the blue layer's opacity to 0, the size to 0, and the green layer's x value to 500? And all of that is also done simultaneously and in an atomic update, so you don't actually see partial frames showing up. So let me just quickly go through some of the examples in Leopard itself. I list a few here, and I'll go through a few of them with more screenshots and with more detail. One thing to remember is the dock on Leopard is actually a full-blown core animation application. So it's actually doing all of its effects through core animation. So it gives you a sense of the power of core animation right there. We've got things like the icons and the reflections in the dock itself of the icons. Then you've got the stacks feature, which is really great. I mean, you sort of specify the animation if you've seen associated with it. It sort of flows out. It's very easy to do with core animation itself. Start value, end value, and let core animation handle it animating across a path for you. You've seen Time Machine, a few times already in this. At WWDC in DC already. And here you've got all of these windows, Finder windows. They're actually core animation layers themselves. Preview is yet another great example of this. Preview takes advantage of this another feature of core animation called tile layers, which is new than last year's WWDC. And what that really allows you to do is handle large image data set. And so you'll get call back to handle each one of these subtiles as needed. But it allows you to handle larger than 2K by 2K image files across multiple across all of the GPUs that we support. Preview also has great slideshow features that take advantage of core animation. Finder's Quick Look is also taking advantage of core animation. You've seen demos of this, so I won't go into this in too much detail. But X-Ray, here's another example. X-Ray's got a cover flow view itself also. You have several runs, and you want to sort of visualize them and sort of see all of them present at the same time. Here's a great way of actually taking advantage of core animation. So let me actually go over and talk to you and show you a demo of two things. One of them is already available to you in your seed, which is CovertFlow, which is nothing more than a simple way of doing cover flow in your application. So you've got access to this already. I recommend you play with it and sort of to get an idea of how core animation is done directly at the core animation level as opposed to the AppKit level. It's doing nothing more than basically taking all of your desktop images, and you can sort of, as you expect, you can sort of cycle through these seamlessly and with high frame rate. As an exercise, I'd recommend maybe what you should do is sort of play with it and try and changing it. So maybe the center one is a larger size, or sort of apply an animation to the entire group of these layers. So maybe do something else with it, make it bounce up and down, or whatever you want to try. But that's left as an exercise for you guys to do. The other demo I wanted to show you is Core Animation TV. So I want to thank actually the BBC Motion Gallery for most of this content. So the goal here is you're watching TV, and so we've got a heads-up display that allows you to sort of go through different channels and at the same time different shows in those channels. So it shows you the power of core animation right there. And as you notice, we can do things like have all of these movies coming in with different transitions. At the same time, we can also do, bring in the channel list and select any channel you want. We've got 4 or 5 channels here. Let me go into the selection of the shows associated with that channel, and then we can sort of choose that. So the goal we wanted to show you here was just QuickTime content being played in the background, and then with different content on top of it. A lot of this is actually implemented through Core Animation scroll layer feature, that allows us to sort of scroll around in this larger space and have all of these layers sort of show up appropriately. So we've got a Quartz Composer composition running in the background here. At the same time, we can also start putting in new content. So here we've got a layer, a series of layers. I mean, the actual layer itself is actually that thing there. But we also put other layers on top of that to sort of help out with some of these other controls. For example, you'll also notice that in here I've got core image filters being applied to some of these buttons. So there's a bloom effect sort of being applied there. And in this case, the clock is actually done as a Quartz 2D content. Every second, it's actually drawing the clock hands appropriately. There's other things you can put in here. And after this session, I hope the stock price does go up to that value. Other things here. And then you can also do GL content in here. So let's say I wanted to have that stick around. Oops. I'm back here. So it shows a great way of how some of these different technologies can be sort of incorporated together into your applications. So let me go back to slides. And at this point, I'd like to invite John Harper to actually go over some of the details associated with core animation itself.
Thanks, Varun. OK. How does this work? OK. So the first thing to bear in mind about core animation is that it's a little different to some of the APIs we have in that it's very much data-driven. And what that kind of means is that most of the time, you're not really thinking about the functions to call or imperative-type programming, but really how to kind of control and define the description of what you want to see. So we've talked about layers and animations, and So this basically means that the layers are just kind of a property-based object with a bunch of properties and a bunch of sub-layers and all this kind of stuff. And the way you drive the framework is just to set the properties and configure the objects and let the engine take up all the strain and do the work in the background. And so we take a lot of advantage from the new Objective-C features. So all of the APIs defined in terms of Objective-C properties. This gives you some nice things in terms of subclassing, but mainly you get the nice dot syntax, which we all love. And then because it's a data model, we have to kind of define what this means in terms of getting the changes to the screen. And the way we do that is that we define these things called transactions. And a transaction, all you really need to know to start with is that a transaction includes all your changes from each iteration around the event loop. So you can change whatever you like, and at the end of the event loop, we collect all these things up and push them to the screen in a single update. OK, so let's go through in a little more detail now how each layer is constituted. That's a word. So first of all, each layer has some geometry. So they have a rectangle which defines their own kind of coordinate space, the bounds. They have a position in their containing space. And some other properties, like they can have a curved corner or a transform putting them into a 3D space, and a few other things which we'll leave in the header files. Once you've got the geometry, then we look at the kind of the four main things that make up the image of the layer. And the first thing, which excuse me, is drawn on the bottom of the stack, is the background color. And obviously, the background color sits in the coordinate space of the layer and follows the rounded corners and that kind of thing. On top of the background, we put the content, and this is the stuff you draw or the image you give us. And there are a number of ways to kind of define how that content is mapped into the layer geometry, because, for example, the image may be bigger or smaller than the layer itself. So you can tell us, align to the top left or the bottom right or resize or whatever. Contents rect we'll get to later. So then on top of the contents of the background, you get the sublayers, traditional kind of recursive sublayer, subview compositing model. The one slightly different thing here is that the sublayers can actually extend outside their parent. You can tell them to clip or not clip. We'll get to that later as well. Click. Once you've got the sublayers, we come to the border, and the border is not often used, but sometimes it's useful. And it just gives you a ring around the edge of the layer, and you can define the color and the width, and that's about it. So now we have this thing. We have the background color, the contents, the sublayers, and the border. And this gives us the basic image of the layer. So the next set of properties kind of tell us what to do with that. And the first thing, which we talked about a bit already, is you can apply core image filters. So you can give us an array of filters which are applied in order to just kind of take the original image, push it through each filter in turn, and give us some output. In this case, we're using a morphology filter. You can also have a shadow, which has the standard kind of configuration. In this case, it's red for some reason. And once you've got that, the final thing you often want to set is the opacity. OK, so now we've finished with that, and we've got the image in isolation. And then the next thing we do in the rendering model is we composite it into the background, which is kind of everything which was drawn up to this point. And you can use a filter for that, like a blend mode or something. And then finally, once you've got this kind of composited image of the layer into the backdrop, we then can use a mask to kind of clip it or apply it into the original destination. So in this case, we used an Apple mask for some reason. OK. I mean, these are all things you can read about later in the documentation. So we talked a bit about mixing content. And the way we do that largely is by defining a bunch of different subclasses. The CA layer is great for doing the standard kind of image-based CG context-based drawing. But if you want larger data, which actually is bigger than the graphics cards can support, then you typically have to use the tiled layer. Or if you want OpenGL data, you have to use the OpenGL layer, and so on. Yeah. Oh, I should say that the scrolling layer is just some convenient things for scrolling. OK. So like any other object, the way you configure these, the way you deal with these things is you allocate them first, obviously, give you a pointer. And then you typically set a bunch of properties on the layer. So you could, for example, set the background color of your layer to white, and then set its size to 100 by 100, or whatever. And then once you've configured it, the next thing you normally do is add it to an existing superlayer to put it into this kind of recursive compositing tree. Once it's in the layer tree, assuming its parent at the top of the tree is visible, then at some point we get into this kind of transactional-based layout and drawing model, which we'll talk about in the next slides. So once you've gone through the stage and it's been committed at the end of the event loop, it's on the screen, it's being drawn, and you no longer really have to care about it unless you want to change the properties. And of course, finally, you may end up removing it, deallocating the layer. So we can go through that in a little more detail. So the first line is we're going to create that layer. We just use the standard kind of initializer allocator type convenience method. Then in this case, we're just going to say give it a fixed point on screen in its parent's coordinate space, like a little box in the corner in this example. And then we're not going to do any custom drawing. We're just going to say, here's an image, which we presumably loaded off disk or drew earlier, and say, this is your contents for the layer. And in this case, because we haven't told it to do anything else, it'll resize to fit the bounds of the layer. And then, as I said earlier, we have to add it to the layer tree. So we use this convenience method to modify the sublayer's property of the parent of this mySuperlayer thing. And once we've done that, if mySuperlayer is already visible, then we'll get some kind of default crossfade transition, and it'll just appear on the screen. OK, so back to layout and drawing. Two of the main things you want to do with layers once you've created them is position them and then draw into them. So we kind of wrap that up in a way that makes it a little more convenient, and it's very similar to the NSView drawing model in that we give you a way to kind of defer all these actions until immediately before we commit them onto the screen. So layout is the first pass, and this basically gives you a chance to hook in and kind of position all your sublayers somewhere in the global space. And so there's two ways really of defining layout behavior. You can subclass the layer, which we'll show later, or you can assign a delegate. In both cases, you typically call this setNeedsLayout method just to say, I need layout. And then in the subclassing case, you would implement this layout sublayers method. Or in the delegate case, you would implement some other kind of third-party object which implements basically the same method, and then gets called when you set that as the property of layout manager property of the layer. Delegates or layout managers are pretty useful in that you can kind of encapsulate reusable layout algorithms, I guess. So for example, if you know that a bunch of your different subclasses all need a grid layout method or a box, 1D packing or whatever, then you can wrap that up in a layout manager and just reuse that for every layer. We give you one existing layout manager, which is called the constraint layout manager. And this is a nice way to kind of describe kind of spatial layout constraints. So you can say that if I have 5 sublayers, then the first one, his left edge is relative to the right edge of the next one, and things like this. Finally, if you really want to use the old style stuff, we also have the auto resizing mask property from NSView, and that works just like an NSView. So drawing is pretty similar to layout, and it runs, but in this case, you're not positioning things on screen, you're actually drawing into the layers. And I should say here that you don't have to draw into the layers. Like we saw earlier, you can just set the contents of the layer to be some image. And that works in a lot of cases, but also often you want to do custom CG drawing. And so the best way to do that is just call setNeedsDisplay on the layer and then implement the drawing context method. And if you do that, we can create a buffer for you in the optimal format for the graphics card, the optimal size, set it all up correctly, reuse the CG contexts, and then just give it to you to draw into. So the point at the bottom is very important. You should never call setNeedsDisplay unless you're really sure you do need to display. Because if you do, we see this in some cases, you'll end up with a kind of a layer-sized transparent image just sitting in the stack taking fill rate for no reason. What's next? OK, so now we're going to go through subclassing in a little more detail. One of the main reasons to subclass is you want to add properties to layers. So in this case, we're imagining that we have some kind of custom drawing code, but we want to reuse the layer. So we're going to add a line width property. And presumably, we're going to use this when we actually draw into the layer to kind of use some special behavior. So the first thing we would do is in our header file, we would declare this line width property, and we do it in the normal Objective-C2 add property syntax. But the thing to kind of be aware of is that for the most optimal behavior, you really want to let CoreAnimation implement all the properties. So you don't want to do add synthesize or define your own set of getter methods unless you have a real good reason to. The best thing is just say add dynamic in the implementation file, which just tells the compiler, I'm not going to do anything here. And then at runtime, CoreAnimation can introspect all the classes and see, well, this guy didn't implement this property, so I'm going to do it for him. And that basically means we'll create the set of getter methods and all that kind of stuff and manage the properties for you. So the first thing after declaring the property is typically you want to give it a default value. If the default value is 0, you don't have to do anything. We'll do that for you. But if it's not 0, the thing to do is override this default value for key method. And then you can check the key, and if it's your property, then just return some value. This doesn't have to be particularly efficient because we cache the values when we first see the class. So, OK. So once you've given it the default values, the next thing to be aware of is typically most times you add properties, you're doing it because you want to change the layout or drawing behavior. So that means if the property changes, it's kind of convenient if the layout or drawing kind of updates itself automatically. So the way we found that's best to do that right now is you can override this KVO method, did change value for key. And obviously, all property changes will go through this method. And then in the same way for the default value, you can just kind of check for your key and then do something. In this case, we're going to say, if the key is line width, we know we have to redraw the layer, so we're just going to say set needs display. And of course, cool super. Finally here, since we're going to do some drawing, we're going to override the drawing context method, and here we're going to use that property value. You can use your imagination what we're going to draw, because I was running out of space. But basically, you just say self.property and everything kind of works. And that's basically how to subclass. So a little kind of sidestep. The CA layer is great for normal size data, where normal is kind of up to about 2,000 pixels by 2,000 pixels. But if you want larger data or data that has potentially multiple levels of resolution, where that means you may have a representation or can generate one at 50% or 25% and so on, then you probably want to use the tiled layer. And the tiled layer is a really nice way to kind of manage all this stuff asynchronously, in that it doesn't ask you ahead of time for the data. It just kind of waits and sees what's being rendered on the screen. And then we'll ask you kind of asynchronously, like, give me the tiles for region 0, 0, or 100, 100. And the other thing is it also manages the level of detail. So if it sees that you're zoomed right out on this kind of 10,000 by 10,000 pixel layer, then it will probably ask you for a level of detail at kind of 10% size or something. And that means that it can really minimize the amount of bandwidth it's using to kind of put that thing on the screen. Also, of course, it lets you do whatever kind of filtering you want, so you probably end up with a better result. Yeah. So I guess the last point is that we said earlier you can always assign to the contents property, and that's not true here. If you do that, you basically make it a non-tiled layer. OK, so back to animation. I guess the previous session talked a bit about this. But basically, we have the CA animation class to represent all of our animations. And the way the animation model works is that just like the layer model where you describe what you want to see on screen, you do the same thing with animations. You create the object, you set all the properties to describe the animation you want to see, and then you just add it to the layer. Once it's been added to the layer, when its kind of active time approaches, the rendering engine will just do everything automatically. And then typically the animation will be removed as soon as it's completed. So there's two ways you can actually add the animations to the layer, either implicitly or explicitly. And most of the time, we just use the implicit animation, which basically means that every time you change a property on the layer, there's some default animation which is going to run automatically or implicitly. It's very similar to the Cocoa stuff. And the way this is done is by this action for key method, and it's kind of similar class methods. And basically what this does is it calls this method when the property has changed. It kind of gets some default animation, which obviously you can override, and then adds it to the layer for you. And that often gets you about 90% of the way done with your animations. But some of the time, you then want to create a more kind of expressive or complex or whatever explicit animation. So in those cases, you would probably disable the implicit animations and then create some set of explicit animations which define the property change in more detail, and then just add that directly to the layer. They're both doing basically the same thing, so it doesn't really matter which one you use. Yeah, and then when the animation is over, unless you tell it not to, it will just automatically disappear from the layer. You can also remove them by hand. So now we're going to look a little more detail in the classes that let you describe animations. So the base class is the CA animation. And this really just has a timing function which defines kind of ease in, ease out curves, things like that, and the delegate. The delegate lets you get messages back when the animation starts and stops, which can be useful in some cases for chaining things or modifying the layer tree after an animation is finished or whatever. The timing protocol, we're not going to talk a huge amount about, but basically it's a way of describing a timing model which both layers and animations implement. So and the timing model has things like a begin time and a duration, a repeat count, and that's about all you really need to know. So this just means that an animation has a begin time and a duration, basically, for now. So the most common type of animation we deal with are property-based animations. And this is basically because the layer model is very expressive in terms of properties. So the natural way to animate things is typically just to animate the property values. So the property animation, that's basically just the name of the property that's being animated. So deriving from that is then the basic animation, which we also heard about earlier. And the basic animation basically just lets you set a from value and a to value so that you can animate the most common type of property changes, which is, for example, change my opacity from 0 to 1 or 1 to 0. For more detailed property animations, we have a keyframe animation class. And like most kind of animation, motion graphics type things, the keyframe animation just lets you specify an array of values to keyframe through, and with some kind of percentage timing. So you can say that this animation has 3 keyframes, like so opacity from 0 to 0.7 to 1 or something, and then you can specify the relative timing amongst those keyframes. One other interesting thing here is you can also not specify an array of keyframes, just kind of give it a CG path. And this way you can get kind of 2-dimensional motion path animations working pretty easily. Okay, so the times when you really can't achieve the behavior you want by animating the properties of the layer, we have this transition animation subclass. And the transition is really an image-based animation. So it's something like a crossfade, where you can't really achieve a crossfade just by modifying the properties of the layer. So you have to kind of go back to the pixels and really kind of generate those pixels and blend between them. So there are a number of built-in types of transitions, like crossfade or push left, push right, the kind of keynote type transitions. And also, you can just give it an arbitrary CI filter, or sorry, a CI filter that implements a transition. And this means you can extend this and implement your own transition types, which is kind of neat. OK, click. Finally, we often find that having one animation is good, but to get the behavior we want, we really want to be able to kind of collect these things up and animate 2 properties at once. So you could just add 2 animations. But the nice thing about the group is that it lets you kind of define a timing model that all of those animations sit within. So just like an animation has a begin time and a duration, so does the group, which means that when you put things inside the group, you no longer have to care so much about their begin times and end times because they're sitting within the group. So the timing, you can give the group a single timing function, which means that they all ease in, ease out on the same pattern. OK. So I guess these are basically just the classes you normally program to. I mean, you can instantiate the others, but you probably won't see anything useful. OK, so here's a very simple, concrete example of programming the animation model. First of all, we're going to, the same way we do with layers, we're going to create this object, basic animation, and we're going to set its properties to describe what we want it to do. So in this case, we're going to say animate the opacity property of the layer, and we're going to say animate from this value 1 to value 0 over 1 second. And that's pretty much the simplest animation you can have. Finally, once we've kind of set all the properties to describe exactly what we want, then we just add it to the layer. And then, as I described earlier, the next time around the event loop, this will be sent into the rendering thread, and you'll see the animation kind of happen for a second and then disappear. OK. So the other thing about animations that's interesting is they don't modify the layer properties directly. They modify what we call the presentation values. So when you're kind of configuring the layers, what you're really defining is a model, which we then layer the animations on top of to generate the real screen values. So, so then that makes things kind of tricky because often you want to be able to say, well, where is the thing on screen now? And if it's animating, you can't just ask the layer because it has the model value, not the presentation value, i.e. the animating value. So recently we've added these methods called presentation layer and model layer. And what presentation layer does is it basically lets you request a copy of the current layer you're sending this message to, but with all the animations applied for the current, for basically the current time. And so you can then get this presentation layer and then ask it for its opacity. And if the animation we just saw is running, then it would probably return somewhere between 0 and 1, not 1 or 0, which is the final states. And so there are a couple of places where this is really, really useful. The first one is probably hit testing. The other kind of interesting thing about the presentation layer is that it's not just one layer. It kind of defines a presentation tree. Because if you ask the presentation layer for its sublayers or its superlayer, then it automatically generates the presentation values of those layers as well and gives them back to you. So you can just kind of create the presentation layer and then say hit test. And that will actually hit test across the entire presentation tree. And then we'll find whichever layer in its screen position contains the point you're asking for. And so then we send that result, the model layer message, just to get back to the kind of the things we know because we created them, which are the kind of the object model layers, the layer tree layers. And this works because Cocoa defines pretty nice behavior for sending messages to nil, at least for pointers. So the other use is that we can ask a layer for its presentation layer and then query the value of the property we're about to animate. So when you change the position of a layer and we go off and generate the default implicit animation, we actually set the from value of the animation to be the position from the presentation layer. And that's because when you change the value of something while animating, you don't want to animate from where it was kind of half a second ago. You want to animate from where it is now. So that's that. OK, so now we're getting on to more kind of low-level things. So the first set of points about how to make core animation applications faster is that since we sit on top of OpenGL, if you know a little bit about how the graphics card works and how OpenGL kind of talks to the graphics card, you can theorize about how you might make the application faster. So the first thing is you want to minimize the amount of geometry that gets sent to the graphics card. So that obviously this means minimize the number of layers in some cases, or also, if you don't need it, disable the edge anti-aliasing we do for you, because this generates more geometry. This is typically not a big deal, but we mention it for completeness. More importantly, you really have to kind of think about overdraw. Overdraw is a measure of the number of times we touch each pixel on the screen. So for example, if you have 100 layers composited on top of each other, and the engine doesn't know they're all opaque, then it's going to touch that pixel 100 times. And that's going to consume a lot of fill rate, even on modern graphics cards. So the way to kind of fix this problem is to either implicitly tell us that the layer is opaque by giving us an opaque image to put in the layer, or just there's a method on the layer called opaque, which you can kind of override to return true or set the property or whatever. And when we know that the layer is opaque, we'll try not to draw things underneath it, which drastically minimizes the amount of fill rate. Similarly, you want to minimize the amount of texture or image data you send to the graphics card. So for example, if you have 1,000 layers and they all have the same image, then you shouldn't generate 1,000 copies of the same thing. You just use one image and set it as the contents of that layer. And then we'll create a single texture which gets past the graphics card once and probably sits in the texture cache. Another kind of facet to that is that you can take things further by saying that if I know that this layer, even though it's 1,000 by 1,000, if I know that when it comes out on the screen, it's only going to be 10 screen pixels by 10 screen pixels, you really don't want to give us that 1,000 by 1,000 image. You want to give us a 10 by 10 image, because that way we're just also minimizing the amount of texture data. Finally, this is a little harder to understand, but basically OpenGL works a lot better if you don't tell it to change all the time. So all you really need to know is that if you can kind of group similar layers together. So by that I mean, if you have 100 layers all with the same image, then you might want to kind of put them consecutively in the sublayers array, because then we don't have to kind of give OpenGL that image and then another one, then back to the first one, and all this kind of latency generation stuff. So that's the kind of basic stuff. But the other big kind of performance killer that we see is that you can render things off screen a few times. And what I mean by that is that often we can't just tell OpenGL to render this layer straight to the screen. We may have to render it into an off-screen buffer, apply some kind of manipulation off-screen, and then pull it back on-screen. And it's pretty, it can kind of cause your performance to drop pretty rapidly. So there are a number of things you want to avoid if you want to kind of go for this kind of top level of performance. One of which is you should try to avoid group opacity. Group opacity effects are where you have a number of objects, all with a single opacity value applied to them. So for example, if you have a layer and it has 5 sublayers, but you change the opacity of the superlayer to be 0.5, then really the only way we can render that correctly is by taking those 5 layers, rendering them all off screen into a buffer, and then taking that buffer and blending it back on screen through the opacity, because otherwise you get a different result. Similarly, any use of masks can be expensive, especially mask layers where you have to render the layer off screen to generate the mask, or if you just set the mask to bounds property and the bounds of the layer isn't pixel aligned, by which I mean it's not integral or it's rotated or something like that. It probably doesn't come as much of a surprise that if you use core image filters or shadows, you also incur some off-screen rendering penalty. Finally, if you get really into the 3D stuff, then if you try to put a 3D layer within another 3D layer, because of the way we define our rendering model, that will be flattened into an off-screen buffer between those two transforms. So you really want to use one level of 3D only. OK. So here we have a large number of general kind of hints and tips, just things we've accumulated over the past couple of years as we've been using this stuff. The first few really deal with animation. And we found the best way to kind of think about animation and kind of how we write our apps is we just kind of deal with the properties first and get it kind of looking right on screen. And then we let the implicit animations kind of do their job, and we end up with something that probably looks OK, may not be exactly what we want. So we get 90% of the way there just by setting properties and letting the implicit animation engine run. And then when we have to go the extra mile to get exactly what whoever specified the UI wants, then we can turn off some of the implicit animations and kind of put the explicit things we really, really know we need in their place. The way to do that is you can set properties on the transaction class to say disable implicit animations from here to here. So it's pretty common. The next point is that the timing model is something that's often overlooked, but you can use it to kind of stagger things and kind of arrange things in time as well as space. And this lets you kind of take something that looks very simple in code, i.e. like one animation does the same thing, and then apply it to, say, 1,000 layers with slightly different time behavior. It gets something that looks pretty complex. And this is something we've used a lot in the demos we've showed at WWDC. Similarly, you can take advantage of the fact we have pretty good code to interpolate matrices. So if you want to kind of animate something through a path in space with different orientations at different points, then you can often just kind of define a transform which represents the orientation at those points in the keyframe. And then the animation engine will take those keyframes and kind of just interpolate between them, often in a way that's pretty nice. A lot of the kind of camera animations you see in the 3D demos we show really are just kind of interpolating matrices with nothing else actually going on. So that leads into the next point, which is that when we do these 3D demos, we really just use the sublayer transform property, which is another 4x4 matrix, but applies to the sublayers of the layer. And then we use that to kind of apply the 3D perspective and camera transforms. It's kind of like the projection matrix and the model view matrix are kind of combined into one if you're familiar with OpenGL. This other tip is a little kind of hard to understand, but basically you often want to animate the removal of a layer from the scene. And so obviously, if you were just to add the animation you want to see for that removal to the layer, and then remove the layer, you're not going to see anything because, well, the layer's gone. So typically the way we do this is we add the animation and make sure the animation has a delegate. And then the delegate will get the notification when the animation has finished, and then we can go off and remove the layer from the layer tree. There's one more little point to this, which is if we just did that, then we'd probably see, the removal animation run and then a flick back to its original state, and then the layer get removed because of the kind of inherent asynchronicity in the model we have. So the timing protocol gives you a way to fix this, which is you can say, this animation, it's going to run for some duration, and then I'm going to set this fill mode property, which says, even though it's over, keep applying the last state forever. And that just kind of, you can animate some removal thing by, animating the size to 0 or the opacity to 0. And then that final state is just kind of clamped in the timeline in conjunction with this removed on completion thing. And then once the delegate fires, because it's seen that the animation is finished, even though it's really still being applied because of the fill mode, that's when you can go off and remove it and you don't see any glitches. OK. That point is pretty simple. Basically, we also, you may not think about it, but because a lot of the color properties on the layers are defined as CG colors, in most places you can take advantage of the full kind of expressiveness of the CG color, which means you can actually create a tiled pattern. For example, some image, like a checkerboard image, which repeats across the plane. And you can specify that as the color. So this gives you a nice kind of fairly simple way to kind of take an image, or take some rendered cell and repeat it across the background of the layer. Finally, the last one is just kind of a gotcha. For performance reasons, unlike some other Cocoa frameworks, we don't actually do the kind of retain auto release thing when we fetch a property for you. So you just have to be aware of that, basically. OK, so finally, basically 2 lines of code to put the layers on the screen. Obviously, if you're using Cocoa and NSView and mixing that stuff in, it might be a little more complex. But for a lot of the kind of core animation only type demos, then we'll basically have one containing view, and we'll create some custom layer tree and then just set that layer tree as the layer of the view, and then tell the view you have to render using layers. There is another method, which is the CA renderer class. And this is a way to drive the rendering of core animation explicitly. And typically, you probably won't have to use this at all. There's basically 2 places it might be useful. One of which is if you want to drive the rendering on some external timer. So you could say, render every frame and then export it to a QuickTime movie or something. Or secondly, you may want to have like a full screen OpenGL context and just give the renderer the direct OpenGL context and render into it. And I think that's about it. So I'm going to give a quick demo. And I thought I would go through some of the stuff we showed on the keynote, but from more of a kind of how do we do it, or how did we do it perspective. So you probably saw we had this video wall application where I was trying to replicate the Apple TV movie that shows when you start the Apple TV. So the first thing we did was we built this little application that creates this mesh of layers. And whoops. So you can see this bears some resemblance to what we showed yesterday, but it's a lot rougher. And this is basically the first thing we had, in that you can have this kind of mesh, which is basically kind of some number of layers mapped onto the face of a cylinder, each one with some 3D transform defining their position in space and z position, and then some kind of custom layout manager to define the kind of cylindrical layout. And the various parameters we thought we might want to change for the demo. So then we can add some color to this just by doing that. And you can see that this is kind of chunky in the edges of these things. So the next thing is we can turn on the edge anti-aliasing to make that kind of clean up a lot. And then if I go back a bit, we can add the reflection layers just to get that nice kind of pseudo-reflection look. And so that's basically the app. And you can see we have this kind of nice 3D motion, which is, like I said, it's just animating the camera transform or the sublayer transform. So when I do this, I basically just pick a position in space. You can see it actually in the bottom right-hand corner of the app. And I use this to define my camera matrix, and then set that into the layer, and then it all just animates automatically. And I guess the real trick here is that we knew we wouldn't be able to play back like 1,000 movies simultaneously. So we cheated, basically. And what we did is we generated this kind of pseudo texture atlas kind of movie in motion, which has 144 tiles, each of which has one movie playing back in it. And it's like a 20-second repeat loop thing. And so that's that. And then what I can do now is I can take this movie and drop it onto this app. And you see the actual kind of video will start to appear. And so I guess the way we do this is there's kind of a nice little trick here, which is that we can create a single Qt movie layer. And then we know that whatever the layer is, the only way it really has of communicating its contents to the render tree or the renderer thread is via this contents property. So what we actually did is then we created, like if we want 1,000, we create one Qt movie layer and 999 just normal layers. And then basically just copy that contents property after we know it's been initialized to all the other layers. And so they're basically just kind of sharing this movie. And then the other thing we did is that obviously we don't want the entire movie in every cell. So we have this kind of property on the layer called contents rect, which is a way to basically texture map a subregion out of the contents of the layer. So each layer is specifying some kind of subregion of this overall movie. And that's basically that. And obviously we still have all the nice fast motion and all this kind of stuff. And this is basically, I think the entire demo was about 4,000 lines of code. Most of that was to do with the cover flow stuff, and the searching actually was the main part, and the other little bits and pieces. I mean, I think the thing I'm showing you here is probably only a few hundred lines of code. So, okay, I think that is that. Okay, and now I think it's back to Haroon to finish up.
Thank you. Thanks. Thanks, John. So we're actually done. For most contact information, you want to talk to Alan Schaefer, our evangelist, on this part, and the documentation, sample code. So one of the demos that I showed earlier is already available. We'll try and get the other one available to you as soon as possible after WWDC. And we've got a few labs to go to: the Core Animation Lab and the 2D Graphics Lab, both at the same time tomorrow. And you want to go to that. The Core Image one, obviously, and then also the OpenGL one, given that how Core Animation is sort of tied to it.